Hello, today I'm going to solve my homework 10. Following languages are decidable. If a language is decidable, we should give a brief high-level description, TM deciding it, otherwise prove that language is undecidable. In all cases, let M be deterministic, one head, one tape, Turing machine. Okay. Let's start with 1.
Okay.
Let's speak thinner.
Yes.
L1. X. At some point, in its computation on input X, take it on. Okay, better. Speak thinner. M re-enters its start state. Its start state. Okay. Initial. What does it mean re-enter the start state? Okay. Where is my? Yes. It means that during its step-by-step execution on X, machine M eventually go back into the same state which it began. The start state. Okay. It may or may not have the same tape content or head position, but the internal state specifically is the start state again. Okay. Is it semi-decidable? I mean recognizable. Yes. That's right. Is it semi-decidable? I mean recognizable. Recognizable. Yes. We can simulate M on input X step by step. If we ever see that M has just transited into its start state, we halt and accept. This procedure will indeed find a witness to re-entering the start state. If it ever happens, however, if M never goes back to the start state, the simulation never halts. Thus, we can recognize membership in L1, but cannot always decide it's in finite time. Okay. Is it fully decidable? Is it fully decidable? No. If we try to decide membership in L1, we should have to say no when M never re-enters its start state, but there is no finite procedure that can reliably detect that it will never happen. Okay. More formally, we can reduce the halting problem to deciding L1. Okay. Suppose we want to know if some machine M halts on input X, we construct a new machine. Okay. Suppose, let's write it. Suppose we want to know if some machine M halts on input X. Okay, we construct a new machine that on input X, first simulate M on X. If M halts, then a new M force itself back into the start state. Okay, via a special sequence of transitions and loop forever. Thus, if M halts, on X, then new M does re-enter its start state. If M does not halt, okay, if M does not halt on X, then new M prime, never re-enter its start state. Okay. Hence, deciding whether M prime X membership of L1 would let us to decide whether M halts on X, which is impossible. The halting problem is undecidable. Therefore, L1 is undecidable. Okay. L1 is not decidable, N1 is recognizable. Okay, L1 is not decidable, L1 is not decidable, L1 is semi-decidable, recognizable. Okay, I will stop recording. Let's open new page. We have finished one question and we will continue with the second. I am pausing because my video recorder doesn't allow me to record more than 10 minutes, so that I will stop video and continue with the second question. Okay, let's continue with the second question. L2, sorry, open M on all accepting inputs aim takes more than 121 steps. Okay. Membership in L2 says for every input X that M accepts, it takes strictly more than 121 steps to accept. Equivalently, one can say there is no input X. Okay. Equivalently, this is important to prove that. Okay, So let's pick a red color. It's hard word, sorry. One can say equivalently. I think it's true. I will check in Google Translate. Okay, sorry, I don't know English. There is no input. X for which m or that m except in one or fewer steps to accept. Steps to accept. Okay. We should construct this. Okay, it's crucial to solve this problem. Then, hence the complement of L2 is, let's write L2 complement. By the way, I forgot timer. Let's start at 8 minutes. Okay. I start timer to don't forget record time. Okay, there exist some input x that m accepts in at most 21 steps. Okay. Then is L2 decidable? Okay. Then we should ask this. One. Let's see one. Let's pick a good color. Let's say is L2 decidable? Look at the components L2. Okay. To show that L2 is undecidable, okay, it is useful to notice that L2 complement is there is an x such that m accept in less than 121 step. That statement is easier to semi-decide because we can systematically enumerate all possible input x, say that Lex order or order by length. For each input, simulate m for at most 121 step. If within 121 steps on some input x that machine m accepts, we halt and say yes, we found such that x, okay? This algorithm halts whenever m belongs to L2 complement. Thus, L2 is recognizable. Okay. Why L2 complement is recognizable? Okay. L2 complement is I'm the semi-decidable. Let's write in the which we seen in the lesson. Recognizable. Why? L2 is not also recognizable. Why L2 is not also if L2 were also recognizable, then L2 would be decide because language is decidable if if it and its complement are both semi-designable, but there is no effective procedure that its finite time verifies. M takes more than 121 step, also all accepting input, since you would have to check infinitely many potential input to be sure no short acceptance ever occurs, okay? Hence, L2 is not decidable. L2 is not. We conclude that L2 cannot be decided by TM. If it could, its complement L2 being recognizable would force L2 be as well, making it decidable, okay? But that contradicts standard undecidability argument, okay? For question 2, L2 is not decidable. L2 is not decidable. And its complement is semi-decidable. So L2 itself co-recognizable, but not recognizable, okay? That's it. Thank you for watching and sorry for late submission. That was tough question. It is good to be solve and understand and show our work. Okay, thank you for your time. See you.